Hello everyone, I am Maksuda Aktakala Monica, a recent master's graduate in production and materials engineering from Lund University. Today, I'd like to present my master thesis on brake particle emissions from freight trains. This research is a finest example to bridge between industry and academia. From the industry, Green Cargo provided us all sorts of material and financial support, and Lund University was our academic partner, allowing us to utilize its laboratory accessibility. Now, in introduction, I would like to draw your attention on particulate matter and its relation with train brake wear. The term particulate matter or particle pollution is a complex mixture of airborne particles and liquid droplets, which is composed of sulfate, nitrate, secondary organic aerosol, sea salt, black carbon, mineral dust, and water. PM can originate from many different sources, such as residential fuel burning, transport, power plants, agriculture, waste burning, industry, and natural sources. Our focus is to study the PM emission from freight trains' mechanical braking system over here. From research, it has been estimated that approximately 50% of total brake wear is emitted as airborne PM10, and the rest deposited on the road or attracted by the vehicle. Another study found that the average proportions of PM 2.5 and PM 1 in the PM10 emission were 87.5 and 68.46% respectively. Scientists have also found very high mass concentration levels of these non-exhaust particles in enclosed environment, which raised worries among researchers regarding air quality and its effect to environment. They also emphasized the need for emission mitigation measures. However, the effective action has yet to be taken because of lack of relevant knowledge. Here in figure 1, you can see different PM by its size. PM10 are coarse particle matter that found near roadways and dusty industry, and which is in size of 10 micrometer and less than that. PM 2.5 are the fine particulate matter that found in smoke haze, which is 2.5 micrometer and less than that. PM.1, known as the ultrafine particulate matter, which is zero point 0.1 micrometer and less than that in size. Furthermore, PM.3 particulate particles with a diameter of zero point 0.3 micrometer are known as quasi-ultrafine particles, and the majority of PM particles are formed in the environment by chemical reaction between contaminants. In figure 2, it shows the health effects of particulate matter as mechanisms of injury. Several studies have showed that short-term and long-term exposure to PM 2.5 is harmful to human body by causing a variety of health problems such as premature death in people with heart or lung diseases, non-fatal heart attacks, aggregative asthma, decreased lung function, and increased respiratory symptoms. Ultrafine particles can further enter the bloodstream by penetrating the respiratory system, which makes them even more harmful than larger particles. The map in Figure 3 shows annual average PM10 levels across Europe in 2023. Red areas over here, including regions in Turkey, the West Balkans, and northern Italy, exceeds both the UE 2030 limit, which is 20 microgram per meter cube, and WHO guideline, which is 15 microgram per meter cube, including serious air quality issues. This hotspot shows the need for stricter control of non-exhaust emission, such as those from train brake system. Aims and objectives. This experimental research aims to study the friction, wear, temperature, particle emission, and SEM and EDXS analysis of two pad friction materials used in freight trains. Identifying effective brake material with longer surface life and lower brake emission is the goal of this research. Here, figure 4 shows the total experimental setup for this project, which we will discuss in detail in upcoming slides. The principle of train braking system is to convert all or part of the kinetic energy of the moving vehicle into other form of energy like thermal, electrical, sound energy to reduce the speed. It actually facilitates to put the vehicle in a stationary position. It also helps to maintain the vehicle's constant speed and to keep the vehicle on an inclined track with environmental influence such as wind and rainfall. The amount of energy produced by braking is tremendous. The amount of energy that must be absorbed when this train is stopped from its maximum speed, like 300 km per hour, is like 1.77 in 10 to the power 9 joule. In railway vehicle, two types of braking method are used to absorb this energy, which classified as adhesion and non-adhesion braking, which shows in figure 5. Train is slowed down due to adhesion between the wheel and the rail in adhesion braking. The basic braking devices used by mechanical braking system are wheel tread brakes, wheel mounted disc brakes and axle mounted disc brakes, which shows in figure 6 and 7. So why mechanical brakes? Mechanical brakes are used for effective because they're effective at low speeds. They're essential for emergency braking and backup for system failure. They also help to complete stop functionability, or they also are used as supplementary braking support. So, due to the frictional resistance between the brake pad and brake disc, mechanical disc brake are subject to considerable wear, while electrodynamic brakes are less susceptible to wear. However, as the effectiveness of the electrodynamic brakes is speed dependent, mechanical brakes are still needed for additional braking, especially at lower speeds. It is said that below 60 km per hour, the friction brakes are engaged to provide supplementary braking, and that at speed below 20 km per hour, the mechanical brakes takes over the entire braking power. So the mechanical brakes are also important in case of malfunctioning of the electrical braking system, or if the train velocity needs to be reduced rapidly, such as in case of emergency. Mechanical brakes are also useful at low speed where the train needs to bring in a complete stop position. And why disc brake uh, over tread brake system? Like we select for better heat dissipation, reduced wheel wear, improved braking performance independent of wheel condition, less noise and for vibration. We normally use disc brake over tread braking system. Now, another portion of theoretical background of this research. Traffic related sources are major contributors to particulate matter pollution and are generally classified as exhaust and non exhaust emissions. Here, exhaust emissions are caused by incomplete combustion of the fuel or volatilization of the lubricant during the combustion process, whereas non exhaust emission refer to particle emission released from friction brake wear. The interaction between the tire and road interface and the resuspension of road dust. Several recent studies reported that the emission of particulate matter from non exhaust emission is quite higher than exhaust emission, and it is Euro 7 legislation before that the non exhaust PM emission was ignored. Euro 7 regulation sets brake particle emission limits and its testing regulation, which is United Nations Global Technical Regulation on Brake Emission System, which is UNGTR. As per Euro 7, the brake particle emission, mainly PM10, limits for vehicles up to 3.5 tons, which includes passenger cars and light commercial vehicles like small vans and pickup trucks, marked as M1 and N1 vehicles, have been set to 7 milligram per kilometer per vehicle for 2025 and 3 milligram per kilometer per vehicle for 2035 during a standard driving cycle is a standardized test by the United Nations Global Technical Regulation. However, limits on emission levels so far are purely based on the particulate mass per unit volume of air, lacking the consideration for the particulate number, composition, and toxicity. The research community therefore suggests that this should be taken into consideration for further limit values and evaluation. Now we would like to focus on CSRD. What is CSRD? The European Sustainability Reporting Standard under CSRD includes ESRS E2 pollution, which requires companies to identify and disclose emissions of pollutants to air, water, and soil. Breakaway particles, especially PM10 and PM2.5, are considered pollutants to air and must be assessed and reported, especially for automotive manufacturers, railway operators, freight companies, and brake material producers. So, this is important to measure PM emission. In Table 1, there is a comparison of PM10 and PM2.5 emission of light electric vehicles, gasoline vehicles, and diesel vehicles um, from 2016. In Table 2, new WHO guidelines and US standards for selected pollutants as of 2021 has been reflected over here, and figure 8 illustrate the based on human respiratory tract and deposition location of particles of different size. Particulate matter enters our respiratory system through the nose and throat. The larger particulate matter is estimated through coughing, sneezing, and swallowing. PM2.5 can penetrate PM2.5 can penetrate deep into the lungs. It can travel all the way to the alveoli, causing lung and heart problems and delivering harmful chemicals to the blood system. In Figure 9, it shows the fractional contribution by age of death to overall population life expectancy discriminates from PM 2.5 and for selected countries. Now we come to the experimental method. In this study, we have used a Nanovia T50 pin-on-disc tribometer to simulate the sliding process at the freight wagon, brake pad, and brake disc contact, which is illustrated in Figure 10 as the test setup, and Figure 11 shows the real-time picture of pin-on-disc. The pin-on-disc contains a perpendicularly mounted pin and a horizontally rotating disc with a maximum rotational speed of 5000 rpm. The dead weight applies the normal load on the pin-on-disc contact up to 100 Newton. Two brake pad materials which we have used, like one is sintered and composite with grey cast iron brake disc, were tested in a pin-on-disc as per the test plan, which shows in Figure 12, to investigate wear rate and coefficient of friction. Here we get coefficient of friction by dividing the tangential force by the normal load. Tangential force or friction force is generated due to resistance between the pin and the rotating disc surface and is measured directly by a force sensor on the tribometer setup. One K-type thermocouple is inserted to measure temperature variance. Wear mass loss were also measured by weighting the samples before and after the repeated drag braking tests. The purpose of the pre-run over here for first 2 hours is to remove the initial surface texture or characters from pad or disc production. In the real application, the initial surface will be removed in the first several braking. So we will mainly focus on the repeated drag braking data instead of the pre-run data over here. The test material. Grey cast iron is a popular train disc brake material due to its high melting point, its very good heat storage and damping capability, and also good castability and machinability. Alloy steel, stainless steel, cast steel, chromium, nickel, molybdenum cast steel, carbon ceramic composite, reinforced carbon carbon, aluminum matrix composite are also used for train disc material based on different specification. Typical material used in brake pads are copper based alloy, which is prepared by powder metallurgy, organic composites, sintered material, and etc. Among these materials, sintered material matrix composites are preferred over organic or polymer based material for brake pad due to its high temperature withstand capacity, which is over 1000 degrees centigrade. Moreover, compared with the synthetic train brake pad, the powder metallurgy brake pad has good wear resistance, good thermal conductivity, resistant bond and porosity, besides excellent braking power and braking stability. So, also the lubrication material such as molybdenum sulfide is often used to improve anti-rub ability and wear resistance for friction material. So over here you can see in the picture the sintered pad and the composite pads are showed in figure 18, the full set samples, and we have in figure 17 you can see the test sample which we have cutted in required size for sintered pad and composite pad pin. Now we would like to focus on our test results and some discussion over that. In figure 18 is the results from the online coefficient of friction rate over time graph, and figure 19 shows the temperature and time history of the tested brake pad from pin on disc test. Both the graphs clearly showcase the pre-test and drag braking test phase, including cooling period in between those tests. In the beginning of the test, in the pre-run phase, the graph showed that the increase of coefficient of friction for sintered pad starts from 0.25 scale and gradually reaches to 0.64 levels. On the other hand, composite pad had a drastic increment from 0 to zero point 0.6 level and maintained stability over coefficient of friction throughout the pretest. For temperature, in the same stage, both the materials are in increasing trend. However, composite pad temperature rises is higher than the sintered pad. Overall, both the figures show a linear relationship between coefficient of friction and temperature. As the surface temperature rises, the friction also changes. While both materials performed well, the sintered pad handled heat better and provided more consistent friction, making it a more reliable choice for high temperature and long duration braking. In the drag braking test, sintered pad shows a more stable coefficient of friction, which is zero point 0.4 over composite pad, which was zero point 0.4 to zero point 0.5, which shows a slight braking performance instability for composite pad. For both, the material's temperature was increasing throughout the drag braking test. However, composite pad shows higher increment of temperature with the highest peak in 140 degree, and for sintered pad it is 110 degree centigrade. From mass calculation, it was found that sintered pad wear rate was 34% higher than composite pad, which can be related to the above result of sintered pad's more stable coefficient of friction than composite pad. Another test result and discussion is over here in this slide. From the CPC test, particle number concentration data have been generated from both the brake material combination. Figure 20 over here illustrates the variation in particle number concentration, which is PNC, number per centimeter cube in y-axis over time, which is showed in the x-axis region for sintered and composite brake pads. Total 270 minutes test period is shown in the graph, where the first 120 minutes is for pre-run, and between each 20-minute drag braking test there is 30-minute cooling time. In both pre-run and final test, sintered pad shows a more sharp and steady increase compared to composite pad. For sintered pad, the highest value is in pre-run is at the scale of 10 to the power 4 number per centimeter cube, and in drag breaking test, it is in approximately 10 to the power 3 per centimeter cube range. On the other hand, composite pad highest value in pre-run is at the scale of 10 to the power 3, and in drag breaking test it is approximately 10 to the power 2.5. Um, the results revealed that in constant drag breaking, sintered pad has more aggressive wear tendency due to the breakdown of oxidation film at high temperature. In the figure 20, this graph actually also shows a higher particle number concentration for both the materials after pre-run, which is actually due to manually mass measurement of the pin from the POD. Overall, it can be said that based on wear rate and particle emission, composite pads are in better position than sinter pad. However, unstable coefficient of friction and high temperature makes its efficiency slightly down compared to sintered pad. This is maybe because of in sintered pad, secondary contact plateau takes some time to form. Until this form, the interaction is rough and unstable, generating many particles. So, composite pads often also containing resins and softer fillers which form the transfer layers more quickly, which also helps reduce particle generation early. Now, figure 21 illustrates here the mass weighted particle size distribution for the sintered and composite brake pad materials respectively, obtained using the GRIMM mini Ross spectrometer. Over here, x-axis shows the particle diameter, which is in nanometer, and y-axis shows the mass concentration of particle for a logarithmic size bin in microgram per meter cube. Both the graphs have two distinct peaks, which indicate two dominant particle size range for this test. For both the material, the first peak is at around 600 to 800 nanometer, and the other one is at 4 to 5 micrometer. But for sintered pad, the second peak exceeds 3.25 microgram per centimeter cube, which indicates the existence of coarser particle like PM 2.5 to 10 in this region that dominates the total mass concentration for this material. For a composite pad, the dominant peak reaches much higher than sintered pad, which is 4.8 to the power minus 1 microgram per centimeter cube, but the intensity or size distribution in this range is in much lower side than sintered pad. Hence, sintered pads showcase wider mass weighted size distribution and coarser particle size than composite pads in the drag breaking runs. So we can question that why sintered pad shows wider size distribution. Maybe it's due to material composition. Sintered pads are metallic and more abrasive. The harder pad disk interaction in sintered pads produce more diverse particle sizes, and also poor friction film formation like sintered pads often take longer to build a stable friction layer, which leads to ongoing direct abrasion at multiple scales. These slides contain another test result with some discussion. In mini-RAS data, we get these test results, which you can see in this slide in figure 22 and 23. Mini-RAS also generates PM mass concentration profile of coarse PM10 and fine particles PM2.5 over the testing period. Here in figure 22 and 23 shows PM10 mass concentration results over time for sintered pad and composite pad, respectively, in figure 22 and 23. In pretest, both materials shows a gradual increase in the PM10 mass concentration, where sintered pad reaches up to around 500 microgram per meter cube, and composite pad finds its peak at 150 microgram per meter cube. For drag baking test, both the pad shows almost similar trend but in different data level, with one top peak and other unstable movement. For sintered pad here, the top peak is around 150 microgram per meter cube, and for composite pad, this peak is around 60 microgram per meter cube. For composite pad, in first drag test, a higher peak is visible, which is due to opening the pin on disk ribometer for manual calculation of pin weight. So this peak can be ignored. So these results interpret that within a specific time range, the total mass concentration of PM10 for sintered pad is higher, that is almost double PM10 than composite pad material. Over in this slide, figure 24 and 25 shows PM 2.5 mass concentration values for sintered pad and composite pad material, respectively, over time in mini-res. Mini-res is, I already told you, it's a wide range of aerosol spectroscopy device. This data is quite similar to coarse particle data, where in pre-run, sintered pad reaches up to around 390 microgram per meter cube, and composite pad finds it peak at 65 microgram per meter cube. For drag breaking test, as like as previous data of PM10, both the pad show similar trend for all the three tests. However, sintered pad was consistent with the level in around 50 microgram, and composite pad was consistent with the level in around 45 to 50 microgram. This can be interpreted that within a specific time range, the total mass concentration of PM 2.5 for sintered pad is slightly higher than the composite pad material. The above PM results seem quite similar with the previous test results, as sintered pad higher wear rate over composite attributed its higher particle number concentration, higher mass weighted size distribution, and also higher PM10 level. However, the difference of PM 2.5 for both the materials is very small, and sintered pad also is in the higher side for this particle range. In figure 26 in this slide, different labels have been drawn based on different features in the sample surface. In this figure, both the images of secondary and backscattered electron are generated at 500 magnification for sintered pad PN material to give a high definition feature contrast. The secondary image here mostly provide the topographical features of the sample, marking wear debris, microcracks, and groove. Wear debris are basically the indicator of abrasive and adhesive wear and particle emission in the pad material due to sliding contact between disc and pad. These features relate to sintered pad wear and particle emission as per previous test results. The backscatter electron image in figure 26 shows the primary plateau and secondary plateau, where primary plateau is a loose granule film on the pad surface forms from worn fibers. On the other hand, secondary plateau formed with comparative higher temperature and pressure than primary plateau with denser film of compacted wear debris. In figure 27, it shows the different features of the surface in secondary and backscatter electron image mode for composite pad material at 130x magnification to get a high definition feature contrast. The secondary electron image here shows cracks, furrow, groove, wear debris due to sliding effect between the brake pad and disc material. In comparison with sintered pad secondary electron image, Composite shows less cracks, wear debris, and groove, which is also aligned with our previous result of higher particle emission from sintered pad material. The backscatter electron image in figure 27 shows the primary plateau, secondary plateau formation, void, microcracks, along with the presence of resin matrix and filler particle. Here, the formation of primary and secondary plateau is more scattered and less dense than the sintered pad one, which also showcase the frictional stability of sintered pad from our previous test result in pin-on disc. In this slide, figure 28 shows the sliding direction for both sintered and composite pad during the pin-on disc test, which clearly shows the reason of different surface wear groove formation pattern for both the cases. Now, some more test results come up from the SEM analysis. The total material composition of the pad material was not disclosed in this report due to our partner company's professional confidentiality. However, the EDXS analysis shows the overview of the compositional structure of both the pad materials. The EDXS analysis performed with the help of spot analysis with a backscatter electron image that showed in figure 29. Choosing different position of each spot is very important to get all the different material range for any sample analysis. The compositional data over here in figure 30 shows each material as a distinct peak. The height of each peak is determined by the number of photons with various energy levels. This energy level is actually the gap between shells of the atom, and it makes the EDXS analysis special than other techniques. A complete comparative analysis for both the pad material has been done as per figure 31. This graph shows that the tested sintered material has the highest percentage of iron, which is 35%, and copper, 20% in their composition. Whereas composite pad is dominating by 29% carbon and 32% of oxygen. This initial composition shows that sintered pad is having metallic rich material and composite pad is having organic resin binders and fibers. Sintered pad is also having 9% of zinc as metallic additive, whereas the composite has 5%. Overall, the EDXS data is in line with the pin-on disc and sample particle testing data, which reveals that sintered pad made out of a metallic rich material and therefore its amount of particle emission compared to composite pad is higher. There are some more scope for future research for this project, like we can include of thread breaking material for simulating its various properties. Also, adding some deceleration braking condition would be great to have other to get the other braking effect, and also analyzes the PM material concentration composition would give a different dimension for this research in future. In conclusion, it can be drawn from this research that sintered pad indicate more stable friction and temperature increase in the repeated drag braking than composite pads. The wear rate of sintered pad is 34% higher than composite pad, which also showcasing the stability of coefficient of friction of the sintered pad. Both the brake pads show almost similar particle number concentration in the repeated drag braking test, while sintered pad have doubled PM10 than composite pad in the repeated drag braking test. Sintered pads also showcase wider mass-weighted size distribution and coarser particle size than composite pads in the drag braking runs, while the mass concentration of PM2.5 for sintered pad is slightly higher than the composite pad material. Worn surfaces of sintered pads are mainly composited of metallic elements, while composite pads exhibited a certain amount of non metallic elements besides metals on their worn surface. Thank you so much for watching us.